One thing that you might have noticed about the big list of properties that define a vector space is that we're insisting that there be a zero vector, and we're insisting that there be additive inverses, but we actually didn't insist that they be unique. So that makes you wonder, are they unique? In other words, could it be possible that a given vector space has two additive identities, two zero vectors? So let's let V be a vector space. And let's suppose that we have two elements of V, A and B, and they're both additive identities. In other words, they both behave like the zero vector. So the question is, are these things actually equal, or is it possible that they're different? Well, let's see. The thing about additive identities is that they can show up anywhere, right? If B is an additive identity, then A is equal to A plus B. And this is because B is an additive identity. Okay, but A plus B, that's the same as just B. And that's because A is an additive identity. But now, looking from at the far left and the far right, we have that A equals B. So actually, there's only one additive identity. If you think you have two, they're actually the same because of this argument here. So, but notice that we don't have to assume that we have a unique additive inverse. We sort of get that fact for free, which is better, right? Because we don't have to make this extra assumption. All right, so we know now that the zero vector, the additive identity, is unique, whether or not you want it to be. Okay, what about additive inverses? Well, let's suppose that again we take a vector in our vector space. Suppose that for some vector in our vector space, we have two additive inverses. So U and W are additive inverses. Okay. Well, what additive inverses means, so what this assumption means is that V plus U is equal to the zero vector, and also V plus W is equal to the zero vector, right? So this is what we're assuming. So the question is U equal to W? Right, so is there some calculation we can do and show that U is equal to W? Well, there aren't really many moves we can make. If it is possible to sort of fill in the gap here, really the only tools we have available are the axioms for vector spaces, that big list of properties that vector spaces have to have, and these two assumptions that we made. So, I mean, how could we use these things? Well, if you look at this second one here, the additive identity is right here at 0, and we can make the additive identity show up anywhere we want. So we could add a plus 0 here. So this is just because 0 is an additive identity, but then 0 is V plus W. But remember, vector addition is associative, so we can move these parentheses over here, U plus V plus W. So this is because of the associativity of addition. But look, U plus V, we've assumed right here that that's 0. So this is 0 plus W. Actually, we're using the commutativity of addition here, because here we have V plus U and here we have U plus V, but those have to be the same because vector addition is commutative. But 0 plus W, that's W. So now we have U equals W, so, right, given some vector V, we thought we had two additive inverses, but it turns out that they have to be equal. So this means that additive inverses are also unique, right? So the short answer is yes, these are unique.